Hello everyone, and thank you for joining us today. Welcome to Megger's monthly webinar series. Today's topic is do's and don'ts on insulation power factor testing. My name is Jamie Smith, and I'm the digital marketing specialist for Megger North America, and I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter and panelists today. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read those questions out during the Q&A segment at the end of the webinar. All webinar attendees will receive 1 PDH or 0.1 CEU for attending. We've also been approved by NETA that all attendees will be eligible to receive one credit through them as well. You will receive this in an email within 2 business days of the webinar, and that email will also include a copy of the PowerPoint presentation and a link to a video recording of the webinar if you'd like to watch it again or share it with your colleagues. Remember, you can ask questions at any time during the presentation, and they will be answered at the end of the webinar. Okay, and our presenter today is Jill Duplessis, and she is a Global Technical Marketing Manager at Megger. Okay, let's go ahead and get started. Thank you for joining us today, Jill.
Thanks, Jamie, and hello, everyone. I'm really pleased to share this next hour and a half with you talking about a subject that has been around me for some time now. I thank each and every one of you in advance for helping make this a successful webinar by joining us today. And I also would like you to know that I appreciate all feedback afterwards, so that we can continue to work hard to make sure that these webinars are a valuable use of your time. In today's webinars, the do's and don'ts of insulation power factor testing, I will start with an 8-slide introduction to set the foundation of what we're talking about with a power factor / dissipation factor and capacitance test. And then we will jump right into the do's and don'ts that I have prepared for you and that I have organized into these categories, starting with safety, then general insulation knowledge, nomenclature, general testing knowledge, specifically as it relates to capacitance and power factor testing, test preparation, test voltage, and then last but not least, analysis. So as I said, we'll anchor this discussion first with a few words about power factor and capacitance testing. This test is a health assessment tool for electrical insulation. I'd like to establish right away that this is just one of several tests to assess insulation. As the slide shows, insulation resistance, dissolved gas analysis, and dielectric frequency response tests provide additional measures of insulation performance and integrity. And each of these tests are necessary for different reasons, and together they provide a much more complete picture of an insulation's health and performance today, and in some cases may even uncover emerging issues. Power factor / dissipation factor and capacitance is what I call a 2-in-1 test. The 2 test parameters, power factor and capacitance, relate to each other and are conveniently measured at the same time, but there's some degree of separation that must be applied to both to understand and to analyze them. So we'll start with a capacitance test and how this relates to insulation. The purpose of electrical insulation is to store electrical energy when surrounded by an electrostatic field. And this is exactly what a capacitor does. So one way to assess how well insulation is behaving is to model the asset with capacitors and then trend the corresponding measured capacitance values with time. So an asset such as a transformer's windings, its grounded tank and core, etc., become the electrodes of a capacitor, while the insulation sandwiched between these uniquely energized parts of the asset or the transformer are equivalent to the dielectric of a capacitor. Since capacitance is describing how an insulation system ideally behaves, and we are monitoring the measured capacitance values with time, we look to the equation of capacitance to learn more about the parameters that may cause a change in capacitance. So if a vacuum separates the capacitor's electrodes, we learned that the capacitance depends only on shape or geometry. Geometric capacitance, as it is aptly called, is equal to epsilon naught times area of the plates of the capacitor and divided by d, distance between the capacitors, where epsilon naught is the vacuum permittivity, or also called the permittivity of free space. But in any event, it is a constant. And the vacuum in this case is called the dielectric, and as an electrical insulator, it prevents charge from moving from one electrode to the other. Now, more often, dielectrics other than a vacuum are used, including various liquids, gases, and solid materials, all of which have very good insulating properties. Depending on the material used, the amount of charge that collects on the plates is enhanced to different degrees, and therefore capacitance changes just by switching from one material to another. This material property is the material's so-called static relative permittivity, or dielectric constant. Dielectric constant is simply the measure of a material's capacitance relative to capacitance should that material be replaced by a vacuum. So we ultimately come to an equation for capacitance equal to the dielectric constant, epsilon r, times the permittivity of free space, a constant, times area of the plates divided by distance separating the plates. Therefore, we can conclude that the capacitance that we measure of an insulation system is sensitive to any geometric changes occurring in the system or significant changes to the composition of electrical insulating materials. And so just two really simple examples. If we have very severe winding deformation in a transformer, whereby the normal distance that separates the, say, high voltage and low voltage windings were to increase, then capacitance will decrease by this equation. And meanwhile, a bulk oil-filled bushing, if that were to develop a leak, whereby a notable amount of oil leaks out and moisture, of course, gets in by the same way the oil leaked out, then the average dielectric constant of the system increases, and then capacitance will follow along and increase as well. Now, on the flip side of capacitance, power factor and dissipation factor are measures of loss. And of course, capacitance represents the energy stored by the insulation. When AC voltage is placed across a typical insulation system, the insulation is charged, but it doesn't hold that charge indefinitely as it would if you applied a DC voltage. In fact, after a half cycle, the polarity of the applied voltage changes, so the energy stored via moving atoms, molecules, and charge, it starts moving back until the next half cycle and so forth. So there's this constant back and forth exchange. And these ongoing so-called polarization processes contribute losses, as does conductivity that results from leakage current. Even when an insulation system is brand new, some energy is lost. These new insulation systems are still typically very, very efficient, but don't store 100% of the electrical energy present across them. And the energy that is lost takes the form of heat, and as I've mentioned, losses can be broadly grouped as either polarization or conductive losses. It basically all boils down to the vector diagram shown on this slide. When I apply voltage across an insulation system, I will measure current through the insulation system. We'll call that total current. Most of it will be capacitive, representing all of the energy effectively stored, and hopefully very little of it will be attributed to resistive current. Losses, expressed in watts as a unit of measure, are related to the resistive current. And we are interested in the phase angle relationship of this total current with the applied test voltage, which is always assigned a 0 degrees reference phase angle. As the resistive current goes to 0, we have no losses any longer, and power factor or dissipation factor is also equal to 0. And as an insulation ages or becomes contaminated, the resistive current increases and power factor, dissipation factor will often increase too. Since we are measuring the losses anyway, a logical question to ask would be, hey, why are we even looking at power factor or dissipation factor? And the answer relates to size. An insulation system, for example, twice as big as another, but otherwise in the exact same condition, will generate twice as much loss. But you can't directly compare the losses of similarly constructed insulation systems because there's no practical way of quantifying their sizes. In that case, you won't know whether or not the difference you measure in losses is because a difference between the two specimens' sizes or a difference in performance between the two insulation specimens. But power factor and dissipation factor take the size into consideration and reports the system's relative losses. So what do I mean by relative? Well, for power factor, which is equal to the cosine of the theta angle, relative losses means how much energy is being lost by the insulation system relative to the total energy present, which includes both the stored energy and that lost energy. So IR divided by the total current, IT. For dissipation factor, on the other hand, which is equal to the tangent of the delta angle, relative losses means how much energy is being lost relative to the energy being stored. So with that, hopefully just 5-minute review, let's now turn to the do's and don'ts. Since safety is absolutely first at Megger, I intentionally chose to lead with this category. And these that I'm about to show you are some safety do's and don'ts specifically around performing power factor measurements. But I want to forewarn you that my list is definitely not exhaustive. For example, I don't even broach ladder safety, which is definitely part of testing. In fact, I've taken entire classes just on ladder safety alone, so please understand that this wasn't the intention of this category, but was rather to emphasize that particularly in our industry, and definitely when it comes to testing, we should continue to keep safety as part of all of our conversations. So beginning with safety do's, do hold a tailgate meeting before each test job. We naturally raise our safety awareness when we talk about what we're about to do from a safety perspective. And these meetings challenge us to think of hazards that haven't been identified. Other colleagues, in fact, may open our eyes to risks that they closely identify with because of their unique experience that isn't so familiar to us, and vice versa. Do check grounding. The asset under test should be grounded well. And do inspect test equipment and leads for damage or excessive wear before use. Do connect the ground lead to the test instrument first before any other connections, and remove it last when testing is complete. Do make it a habit to touch each terminal with a grounding stick before moving test leads to discharge any potential stored charge which may be present. And do stay aware that energizing a transformer winding with an AC source will induce voltage on its other winding. So depending on where you are, you don't want to unwittingly become part of the circuit on the other winding. For example, if you were to pocket a wrench and stuff it in your back pocket and inadvertently catch the wrench on a winding shorting lead behind you during this test, you'll get zapped really good. So be aware of hazards that you are placing yourself around. Don't ever take safety for granted. And don't forget that only qualified persons are permitted to perform tasks such as testing. Part of that qualification is going to be extensive safety training. Don't overlook that improper use of electrical test instruments can result in shock or electrocution, as well as creating an arc flash incident. There's never been a fatality associated with testing with a Megger power factor test instrument. But I'm sorry to say that not all manufacturers of power factor test instruments can say that, so please be aware. Don't cheat a comparative ground circuit relay. It compares the test instrument supply voltage ground to the assets ground, which is brought to the instrument via the instrument's ground lead. And this relay checks to make sure that there's not too much of a resistive difference between the two. And whatever you do, don't grow complacent or allow yourself to become distracted during a testing job. The next category of do's and don'ts pertain to general installation knowledge. Installation is the patient, and there are a few things that we should know about it. So do be automatic about what the gold bar should be for electrical installation. It will perform best when it's clean, when it's dry, when it's relatively void-free, and when it's used within the designed temperature range. I witnessed the end results of a misapplication of a brand new, just your basic garden variety capacitance graded bushing. The application called for a high temperature rated bushing, but this bushing just happened to be used instead. Systematically, within 6 years, the bushing went from brand new to degraded to the point that it was no longer safe to keep in service. Do be wary of the enemies of insulation. These include heat, moisture, and oxygen. And while these may, of course, be external stresses, keep in mind that as an insulation degrades, these are also natural byproducts of the degradation process. Also remember that losses in the insulation manifest as heat, and heat causes further degradation, and therefore more losses, and then more heat, and so forth. So you can get caught in this vicious cycle of heat loss, and so forth. Do remember that electrical insulation fails when the stresses present exceed the insulation's withstand capabilities. And I'm really sorry for my simple visual aid here, but I like it simple. So we start off, the manufacturer, of course, designs the insulation system so that there's a very comfortable margin between anticipated stresses and the insulation's withstand capabilities. And as a brand new constructed asset, it should begin its life with a very healthy withstand, sufficiently dry, ready for battle. But transfer materials such as oil, paper, and press board are organic materials, so it's inevitable that they will age and reach their end of life. While it's entirely possible that external sources of heat may increase during a transformer's lifetime, such as by unanticipated increases in loading on the transformer, as we discussed already, aging will also lend itself to an increase in these stressors. As I've said, failure occurs when the stresses present exceed the withstand capabilities. And we care about dielectric failures in particular, not only because they destroy our asset, but also because statistically, dielectric failures result in more fires than not. You know, the impressive ones that we watch on social media afterwards, unfortunately. Which brings me to the one don't that I have in this category, and that is don't be a bystander. Testing and maintenance allows you to influence the withstand curve. Testing allows you to determine if the transformer is wet, and maintenance is performed to dry it as appropriate, or to recondition the oil if testing deemed it necessary to do so, etc. You can influence the external stresses too, such as reducing loading on your transformer and therefore dropping the temperatures that the transformer sees by thinking twice about how wet you will allow your transformer to operate, because water accelerates aging, carries other scary consequences too. And also by improving the transformer's preservation system, such as by repairing leaking gaskets. That could be a source for moisture ingress. The next category is the nomenclature or terminology associated with this test, do's and don'ts. First, don't get bogged down by the use of power factor versus dissipation factor. They're determined differently, but they're very similar and serve the same purpose after all. In fact, they are nearly identical within the realm of where most insulation systems will test. So which to use then becomes a simple matter of preference. But just to give you maybe some schools of thought about power factor versus dissipation factor, The use of power factor spans various applications in our industry, and in fact is often more readily associated with its other uses, like in performing power system studies or characterizing distribution feeder efficiency. So some feel that its additional use to now describe installation efficiency may cause confusion. In fact, I hear a lot from power plant personnel, as one example, who are really less than enthused about the use of power factor for installation assessment. Meanwhile, dissipate means to use something wastefully. Since dissipation factor reports the relative amount of energy that's lost to heat or is dissipated, it could be argued that dissipation factor is a more descriptive name. Its reason for use is practically conveyed to its name alone. And if you remember that dissipation factor is a tangent of the angle delta, the angle delta, by the way, is known as the loss angle. Secondly, don't get bogged down by the use of dielectric versus insulation. They are often used interchangeably because the dielectric is an insulator. The use of the term dielectric, though, conveys specifically that the material will support an electrostatic field while prohibiting conduction. Insulation, meanwhile, has many applications, so when you use it without context, you may be referring to any one of these applications. And I'm showing here examples of electrical on the far left, thermal in the middle, and acoustic or sound-absorbing materials on the right, all used and talked about as insulations. Also, be aware of slang and don't get trapped thinking that there's any more to it than really just a naming preference. So tan delta is often used when referring to a dissipation factor test, and Doble test is sometimes used when referring to a power factor test. And lastly, do keep in mind that when you're referring to tests simply as a power factor test or a dissipation factor test, you are naturally inferring that the test voltage being used is at or nearly at line frequency. Dielectric response methods like dielectric frequency response entail making power factor measurements at multiple frequencies and then considering how power factor and capacitance change with frequency. Now I have some interesting do's and don'ts prepared for this next category, which is general testing knowledge. Do familiarize yourself with history. It bears to remember how we got to where we are today. I personally think that students of history really do have the upper hand. I mean, not only does history arguably hold the best lessons and prepare one for the future, since they do say history repeats, but through time, you find lessons learned can get muddled and information can get distorted. So it can be a good idea to look back. There are early publications dating to the very early 1900s by cable manufacturers about power factor and capacitance testing. But capacitance and power factor testing really took root with the popularization of capacitance graded bushings and called condenser bushings back in the day. Manufacturing problems with these type of bushings weren't being consistently identified using DC insulation resistance methods. So manufacturers ended up turning to power factor and capacitance tests as an alternative. The way these bushings are constructed made them the perfect test specimen for this capacitance and power factor test. They're basically a compilation of many insulation systems in series. And as layers short circuit in the bushing C1 capacitance increases to alert of a localized problem developing in the bushing. So do remember that the test was anchored because of bushings. And this is significant because the takeaways from that specific application, bushing testing, became sweeping power factor test traits, no matter what was being tested. So earlier detection of problems in bushing insulation, meaning earlier than what was possible with DC insulation resistance measurements, became simply early detection of problems in insulation, which in some applications is really grossly overinflated. And very sensitive to moisture contamination, really in the tap compartment of the bushing via C2 measurements, became simply, hey, this test is very sensitive to moisture contamination. And in many cases, this isn't true unless you're repeating power factor measurements at many different frequencies, in other words, performing a dielectric frequency response test. The next general testing knowledge due is to learn and appreciate dielectric representations and test modes. This knowledge will be empowering, and it will greatly simplify power factor and capacitance testing for you. Throughout this presentation, we will be stressing the importance of minimizing the size of insulation you test. Smaller is better. But how can you chop up an asset's insulation system? Well, a dielectric representation is a testing guidepost that shows you how segmentation may be done. And test modes, meanwhile, are your tool with which to segment. Oftentimes, when you're doing a test, you are energizing more than one segment. Perhaps you're energizing the entire insulation system, but you really just want to measure one segment at a time, and it's the test modes that make that possible. For example, in this very simple image to the right on the bottom of the two images, on the right of the slide, you may be energizing that whole pie, but you're measuring just that one red slice, which brings to mind actually a side note for you. When you go to check out an instrument's testing capabilities, or its capabilities to electrically charge a test specimen, keep in mind that what's actually being charged may be quite a bit more than what is required to charge the fragment that you are trying to measure. So previous measured test results may not be describing completely the job at hand for the test instrument. So because test modes and dielectric representations are really important, I have a few more slides to say a bit more about them. So while small insulation segments are the ideal, do keep in mind that a tester may not have control over how far an insulation system may be segmented for testing beyond a certain point. Like with those capacitance-graded bushings I showed a few slides back, I can't stick a test lead inside the bushing and measure every single layer. So a dielectric representation is a diagram that identifies each component in an asset that will exist at a unique voltage when that asset is energized. But it's left to the tester to identify if the component is accessible so that the test lead may be connected. And the number of unique voltages or component groups present will determine the number of necessary insulation systems. So I'm showing the dielectric representation of a two-winding transformer on this slide. You see it on the bottom right corner. You'll note that insulation between each of the identified components or groups, in this case a high voltage winding, the low voltage winding, and the grounded tank and core, the insulation between those is depicted by a single capacitor. Well, this is adequate since all a dielectric representation is doing is providing a guidepost to testing. On the other hand, you have a dielectric model that serves to predict the electrical behavior of an insulation system, so using a single capacitor for that type of diagram wouldn't be adequate. And as a helpful rule of thumb, in order to determine how to test, simply count the number of separable accessible windings. So I have two examples. First, let's consider an auto transformer with an inaccessible tertiary. 3 windings, a series winding, common winding, and tertiary. Okay, right? But how many are separable accessible windings? The tertiary is out. It's not brought out of the tank. We've already said it's inaccessible. And the series and common windings are accessible, but they're inseparable, so they have to count as 1. So for testing purposes, in this case, we have a single accessible winding, so we test it like a single winding transformer. So next, let's consider a more complicated example, the case of a 4-winding transformer with a winding configuration of delta Y, 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 whereby all winding terminals are accessible except for the 3 secondary neutral terminals. the start point of those Ys, are all connected and grounded internally under oil. So the number of practically separable windings is 2. The delta winding, 1, and secondly, the 3 Y-connected secondary windings, which will be tested as 1 winding since they can't be separated. As for accessibility, while the delta winding is fully accessible, the neutral terminals of the secondary group are not, making it impractical to disconnect that secondary grouping from ground. So in this case, this 4-winding transformer still will be tested using a 2-winding transformer test procedure, but with the exception that the results will not be entirely meaningful. In fact, when you'll find when you measure the interwinding insulation, CHL, you'll end up potentially with some negative power factor values because of that Y grouping, whereby the neutral is still left connected to ground. Now let's talk about test modes for a moment. The enabling feature of a power factor instrument that supports test modes is a so-called guard circuit. All current resulting from the application of the instrument's test voltage is going to seek to return to the guard point. And there are 3 possible return paths to the instrument, and this is via 3 leads that are provided with the instrument. A ground lead, which is always in use, and then 2 optional in use low voltage leads, a red and a black. There are 3 test modes: GST ground, GST guard, and UST. And in the GST modes, the specimen under test is grounded. Now these 2 diagrams on the upper right-hand corner, the specimen is not shown, but it would be off to the right of each of these 2 diagrams. So you can see in the case of the GST mode diagram, the leftmost of the 2, the specimen off to the right has a ground close to it. The specimen is grounded. The appended ground or guard designation indicates where the test instrument will internally choose to connect the low voltage leads based on your input. The UST mode, on the other hand, is an ungrounded specimen test. You can see the guard point now is grounded instead. So any current flow on now required low voltage leads, any current flow along those are measured. The ground lead is always used. Not only does it serve to compare the specimen ground to the voltage supply ground, but it's also a current carrying lead used to measure, or in the case of UST, used to guard. So the next testing do is be prepared. Outside test variables will be one of the biggest challenges to deal with regarding this test, and include test temperature, humidity, surface leakage, and the quality of your test preparations. We'll be talking more about each of these in other categories, but it definitely warrants acknowledgement now, because choosing to simply ignore these variables and not deal with them is not an option. So I have 2 don'ts regarding this category, general testing knowledge. The first is, don't ever forget that the success of this test depends on testing the smallest possible amount of insulation. It all comes down to the fact that power factor or dissipation factor represents the average condition of the total insulation system under test. If you take a look at any averaging index, and I've shown a class, so the averaging index in this case might be a class average on the test. Well, the smaller the sample size, in this case number of students, and their respective scores, the smaller the sample size, the greater the influence that a change in one element, such as an individual student score, makes on the whole. If the set's very large, changes in one element may not even be noticeable. So with power factor, if the insulation system is big enough, some localized contamination may be impossible to see. So do take a look at the size of the specimen that you're about to test, because this will help shape expectations of the diagnostic capabilities of this test. A good example is a large single-phase autotransformer with an inaccessible tertiary. The one I have in mind had severe tracking on the collar around the lower insulator of one of the bushings. only one power factor and capacitance measurement to be performed on this transformer. All the windings were connected together and energized for a single winding to ground insulation measurement. And I can personally attest that the localized contamination around this lower insulator collar did not result in any change at all in power factor when comparing before and after test results. Which brings me to a very important point that needs to be made about size. We've talked about the use of power factor instead of losses because relative losses allow you to compare same insulation systems of different sizes. But be very careful not to take this too far. You can compare two different size insulation systems, but remember that power factor on the bigger one isn't as searching as power factor on the smaller one. So it's not entirely scalable. Even with identical power factor values for both the small and the large, it's not safe to say that the two systems are in identical condition. As in the example I just gave you, the auto transformer and tertiary, a serious problem can be lurking behind a good power factor value if the insulation system is large enough and you can't see it. So I would feel much more confident with a low, good power factor test result on the much smaller of the two insulation systems. And then the final don't I have in this category is don't have unrealistic expectations from this test. Increasing levels of some contaminants, particularly moisture, do not result in notable change in power factor or dissipation factor until the level of contamination reaches a certain threshold. And this figure illustrates this point. On the y-axis, we have dissipation factor of 50 hertz plotted actually on a logarithmic scale. You can see the red bubble is at 1% dissipation factor. Just to give you some reference, the green bubble is 0.3% and the orange bubble is at 0.5% on this y-axis. On the x-axis, we have the percent moisture and cellulose plotted. And we are looking at dissipation factor for a new transformer in blue and a service age transformer in red as they become increasingly contaminated with moisture. And what I want you to look at first is the slopes of both responses. They're relatively flat at low moisture levels. And in this region, dissipation factor doesn't increase noticeably. As you can see, moisture is increasing. We're going more and more to the right, but we're not going so far up the y-axis. So somebody relying on this as an indicator will be unaware that moisture contamination is present and trending upwards. It's not until moisture in paper is at least about 2.5% that the slopes marginally start to increase on these tan delta curves, and 3.5% moisture when the slopes notably increase, at which point then you could say that dissipation factor then has heightened sensitivity to moisture. In spite of its sensitivity to moisture that seems to not occur until around 3%, note that when it finally does approach 3%, if you follow that orange dotted line over, the dissipation factor is still only 0.5%, even though moisture content is now at 3%. So for perspective, operators become somewhat weary when percent water content exceeds, I don't know, maybe 1.7%. And by 2.5% water content in paper, they're typically scheduling a process unit to come dry the transformer. Okay, so an additional note on this graph or figure is the divergence or the separation of the red and blue curves at low moisture levels, indicating that a single dissipation factor value may represent a wide range of moisture contamination levels that's largely dependent on how aged the insulation system is. So for example, if you look at the green dot, a dissipation, which is a dissipation factor of 0.3%, that's obtained for moisture content ranging from 0.5% if you were dealing with a service age transformer. If you keep following that green dot to the right, it indicates that same 0.3% all the way up to 2% moisture content for the new transformer. So this presents a challenge since it's not a straightforward task to quantify aging of a transformer. It would not be sufficient for you to estimate the aging of a transformer by looking at its service life or years in service, because the aging in an insulation system is dependent on many environmental and system variables, maintenance, and several other factors that all have a role in how the insulation will age. So test preparations is our next category, and these do's and don'ts were probably what you were expecting. So not to disappoint, I have these two. The first one being to make sure to check that the transformer tank is grounded well. A poorly grounded tank will show itself in your test results. They will look horrific, really. In fact, this is one area where you may see negative power factor results in your measurements. The next is to physically and electrically isolate each winding's terminals or bushings. So electrically isolating isn't seemingly as big of a deal, but in some cases, physically isolating a winding's terminals may be challenging. You may be dealing with a case of very many messy and time-consuming connections. I'm sorry I didn't have a good picture of this. In fact, if someone has one, maybe you can shoot it over to me after this presentation. Or you may have a case where you have rigid bus connecting to the transformer, so disconnecting it might require a lift of some sort. So in these cases, sometimes you'll see the use of what's called a lap connector. And I show that in the bottom right-hand corner of the slide, an image of it. And what that does is it's there to allow you to practically, more or less, physically disconnect from the power grid when you're in a situation like rigid bus. Basically, you're dropping the two side bars of that, I don't know if I can point to it. You drop these two side bars and are left with a tiny insulator separating, separating the transformer from the still connected bus. And then you'll attach a guard lead to the top of that insulator and continue with your measurements to effectively guard out any contribution from leaving bus connected. But what you don't want to do is you don't want to rely on rubber blankets to achieve clearance from nearby bus, because otherwise these blankets become part of the insulation test circuit and they may lead to non-representative test results. So there are four, if it's really impractical to disconnect bus that's attached to windings terminals, there are four consequences that you need to be aware of. The first is that the measured winding to ground capacitance of the insulation system affected. For instance, hey, I can't attach the bus from my low voltage bushings, so CL in this case. The capacitance of CL is going to be larger than expected. Why? Well, because the insulation system of that affected winding, CL, it can't be measured independently anymore. And the bus left connected or attached to that low voltage winding, as my example, introduces an additional capacitance into the measurement. And since this additional capacitance, we'll call it C bus, is in parallel to the affected windings capacitance, CL, the two are going to add, and you're ultimately going to measure a higher, in this case, CL capacitance than expected. The second consequence is your affected windings power factor will not be as meaningful. If we continue with CL, CL will not be as meaningful and can't be presumed to be representative of the low voltage winding to ground insulation only, because that attached bus frame has support insulators on it, and those, in the condition of those insulators, will be included in the measurement too. And since power factor is an average measurement, the condition of that insulation between the bus and ground may influence your, in this case, CL power factor measurement for better or for worse. Could go either way. Thirdly, a problem in the winding to ground insulation will be harder to see because you just made your insulation system bigger. And remember, less insulation is ideal, smaller is better. And in fact, it's easier to find the needle in the hay in the image on the bottom right than it is to identify the needle in the hay on the bottom left image. So I'll give you a hint of where the needle is on the left image. So now you should see it. And then finally, the fourth and last consequence is that surface leakage may especially influence the measurement if you don't disconnect the bus. Now, winding to ground measurements may already be influenced by excessive surface leakage on that winding's bushing terminals in the way of salt contamination, or if you're trying to test while it's snowing outside or raining outside, or never mind rain, even if you have high humidity because you're out there early in the morning and there's all kinds of dew and condensation on surfaces, or you have dealing with a situation where you have contaminants such as fly ash that's collected on the surface of the bushings. Well, now if you append the measurement and now including bust and all of its support, well, the exposed surface area of the insulation included in the measurement increases. So you may have an even, so surface leakage may have an even bigger influence on your measurement than before. Which brings me to this slide, and just a word about surface leakage and when it's most likely to cause a problem when you're testing. I can't really interact with you, but if I could, I would ask you which case shown here is more susceptible to influence from surface leakage and why. And then you would correctly answer, well, the one on the left, because as the surface area of a specimen becomes larger relative to its overall insulation size, surface leakage has a greater probability of being a problem and affecting the measurement. And as a rule of thumb, if humidity is above 80%, really good luck to you getting a good reading, particularly on assets that are most vulnerable, like bushings, bushing testing, or doing testing on instrument transformers, and so forth. And finally, our last test preparation do is short circuit each separable winding by connecting each respective winding terminals or bushings together. If that winding includes a neutral, make sure you short that together with its other bushing terminals. And if that neutral is grounded, disconnect the grounded connection for test purposes. Just remember to reconnect the neutral connection when the testing is complete. Use bare copper or aluminum wire only for shorting jumpers, and therefore make sure that the shorting jumpers have adequate clearances from grounded surfaces. And this may be tricky in some cases. I'm showing a picture here of an enclosure around each individual low voltage bushing, sometimes referred to as dog houses, which make it difficult to short your U-shorting jumpers to short these three low voltage bushings without touching that grounded enclosure between them. So in these cases, you may find that it's simply impractical to short the low voltage bushings, and when you do, you're going to make it worse for yourself than just leaving it off altogether. So there are cases in which you're not going to short the windings. So what are the consequences of failing to short circuit each winding? It basically results in an unpredictable influence on power factor, and that's the problem. The effect is going to depend on the transformer for sure. The influence is variable. Sometimes it will affect it greatly. Sometimes you won't see an influence at all by not short-circuiting the windings. It all depends. But the mechanism at play and what happens is an inductive component is introduced, Isabel, which cancels and changes the apparent capacitive contribution to the measurement. So the resistive current is always unaffected, but because of the change in the capacitive contribution, which varies from transformer to transformer, the loss angle will change as well. And so in this case, we start with a loss angle of delta, and this increases to an angle of delta prime. And the result is, in this case, a higher dissipation factor or a higher power factor. And the concern is because you don't know how much it's contributing, you could errantly forget to short circuit a winding, and it may introduce a little bit of a change and cause power factor to be elevated, but not so much that you think, oh no, I did something wrong with my test connections, and go back and check. And so that now that test preparation error is causing your power factor results to look higher and different than they had been before, and you end up chasing something that you're not even knowing that it's attributed to a test connection error. So we'll move on to the next category, which is test voltage, and have 4 sides of do's and don'ts related to test voltage. The first being, don't be lulled to sleep when test voltage is selected for you by the software. Typically, industry standard test voltage will be automatically provided nowadays once you, the user, provide the winding ratings and configuration of the transformer. Line to ground single-phase test voltage delivered by the instrument should not exceed the line-to-line voltage rating of the winding being energized. And for transformers with a graded insulation system, which means it has less insulation around the neutral end of the winding, the test voltage needs to be kept less than the voltage rating of that neutral terminal. And you'll see graded insulation systems specifically for like distribution transformers that have a grounded white winding, or a single-phase distribution transformer with a neutral. Next, do remember that power factor tip-up may be a useful and revealing diagnostic. On oil paper insulation systems, the expectation is that power factor tests performed at all test voltages that are less than the maximum recommended one are expected to always yield the same power factor result. So in a power factor tip-up test, you're performing an additional power factor measurement at a different test voltage, and the 2 power factor measurement results are compared. An unexpected voltage dependent will indicate that the insulation is either degraded or that there's a problem in the test circuit. Well, many in the industry will just forego this test altogether unless the system they're testing has a known propensity for developing voltage-dependent problems, such as dry-type transformers, generators, or cables. But what you should be doing is take advantage of smart tools that are available now. They remain vigilant when you decide to forego a power factor tip-up test on an oil-filled transformer because of time constraints, but they're still there monitoring. And so called a voltage dependence detection capability, what it does, how it works, is it capitalizes on a noted correlation of an asset that has a voltage-dependent problem, and suddenly the harmonics generated in its dielectric response. So the voltage dependence detector estimates the harmonic content in the measured response and then determines the harmonics created by the test specimen. And if that harmonic content gets too high, it alerts the tester to perform tip-up testing to confirm that a voltage-sensitive issue is present. And then lastly, don't bother with traditional power factor tests on a service-aged oil-filled transformer in the absence of their insulating fluids as a means or a measure to assess moisture and the success of a dryout, even if you're reducing your test voltage to very, very small levels. Because as we've seen, power factor is relatively insensitive to moisture when it's at low levels. And you're assuming if you're drying it out that you've got it to not crazy high levels to begin with. So in that case, risk of a fire outweighs the rewards of any information that is going to be gained by this test. So instead, I would recommend to look to dielectric frequency response testing, which has turned out to be a really good way to monitor the dryout process of a transformer. And our last category of do's and don'ts relates to analysis. So the first one is, do bring some knowledge about the transformer's history when you're preparing to test or preparing to analyze. This could be in the form of loading history or fault records or records of maintenance and repairs. Find and review previous test results as well as other test results like DGA or Gfr, etc., because all of this information is going to help shape your expectations of what you are likely to encounter. Don't ignore capacitance. In fact, you should be assessing always capacitance and current first. If capacitance or current has changed from a previous test, you may not be testing what you had intended, or you are testing what you had intended and the physical attributes of that insulation system has changed notably. But either way, you're going to want to figure all of this out and why it doesn't match before you even start to worry about the power factor test results. And to compare to previous results requires that previous results are, of course, available. And so these may be in the form of factory tests, like factory reports, or in the case of bushings, even stamped on the nameplate. Or you may have previous field tests that can help you out. But transformer winding capacitance should not change really by more than plus or minus 1% from previous. Now, if you're talking about a bushings and a C1 test, then we start to get alarmed if it's over 5% change in capacitance from previous, and in fact will replace the bushing if capacitance, C1 capacitance has increased by more than 10%. Because at that point, it's a likely indication that you have many short-circuited layers in that capacitance-graded bushing, and you're at risk for, imminent failure. But with a transformer, plus or minus 1%, if it changes that greater than that, then it does warrant a closer look. Now next, don't ignore capacitance, even if you don't have a benchmark value. So what do you do in those cases? Well, in those cases, you're looking out for abnormally low current/capacitance results. So for example, for a power transformer, you're looking for something that sticks out to you would be in the order of 1 to 2 milliamps. That would look really odd for a power transformer. Now this occurs for CH or CL. The likely culprits to check for would be poor grounding, a bad test connection, or an improperly designated test mode. And if this occurs for CHL or CHT, it may not be cause for concern. What it may be indicating is that you have a grounded shield, in the case of CHL, between the high voltage and low voltage winding. And in some multi-winding transformers, the winding itself may look like a grounded shield to your test circuit. So for example, if I'm trying to measure CHT, high to tertiary, on a 3-winding transformer, with that low voltage winding sandwiched between the CH winding and the tertiary winding, it could definitely lend itself to a low current value like 1 to 2 milliamps, and therefore a low capacitance value as well. But do be reassured that there are well-developed suggestions for why capacitance may have changed from a previous value, such as given in the table shown here, which documents all the possible reasons for change in CL capacitance. This is an excerpt from Megger's TLM bulletin about power factor and capacitance tests that I'll provide details about at the end of the presentation. But you can see that for CL capacitance, possibilities include, I haven't disconnected the low voltage bus, so I'm testing more, and that parallel extra bus capacitance will cause CL capacitance to increase. Or I could have winding movement. Any kind of geometric change can cause a change in capacitance. Or for CL specifically, my core ground connection may be bad or may be going bad, and that can also result in a decrease in the CL capacitance. The TLM bulletin explains in detail how that happens. Or the low voltage bushings may have been changed to something completely different. Maybe the bushings I had in place, there are no direct replacements for those, and so I've gone to something of a different dimension and size, and so that could cause my CL capacitance to look different. Or my tank may be ungrounded, I may have used an incorrect test mode, or the transformer tank may be drained of its oil, and even though I don't recommend that, I may be comparing something, a test CL capacitance with the oil drained versus filled with oil. For power factor, as that's concerned, do acknowledge general power factor behavior. Remember that this is an index describing how efficiently the insulation is fulfilling its purpose of maintaining electrical isolation between points of different potential within an energized electrical apparatus. With few exceptions, a 0% power factor indicates a system with 0 losses, and a lower power factor indicates an insulation system in better condition than one with a higher power factor. Do note that power factor can be too low, lower than expected, or even negative, and this may be indicating a problem depending on when you encounter it. And finally, do keep in mind that analyzing power factor simply, and I say that tongue-in-cheek, believe me, means looking for a change in value from previous. And why I say tongue-in-cheek is because we'd the next do appreciate that when you do see a change in power factor, assigning a significance to that change is ridiculously challenging because of the limitations of an averaging index. It's impossible to know when you do have a change whether it's due to general widespread contamination, whether it's due to aging, or whether it's due to localized problem. And we really need to know which one, because each of these conditions would be approached differently. And if you don't know which one you're dealing with, you never truly know what to do next. As an example, if you're only working with an averaging index like in a test score, a class test score, and that test score is, the average is 75, there's no way for you to know whether you have two students with the same score, both getting a 75 on the exam, or two students with extremely different scores that average to 75. So on the left case, that would be the equivalent of widespread contamination or aging. On the right, a case of a localized problem. So just a few more words about these three different classes of problems. We care, and it's important to identify localized problems because their presence significantly raises the risk of dielectric failure and therefore requires immediate attention. But not only is it impossible to determine if one exists, a localized problem exists from just the power factor alone, but when there is a localized problem, power factor might not change much at all because of the averaging influence of surrounding healthy insulation. So very small increases in power factor could be the manifestation of a very serious problem in your insulation system. A small change in power factor due to aging, on the other hand, might require nothing more than taking note and repeating the test again in several years. And if the power factor change is due to widespread contamination, it might require remediation, but it might not be immediate or urgent. It may be reasonable to schedule during a more convenient upcoming maintenance period. But if the contaminant is moisture, by the time its presence results in a power factor change, the time likely will have passed when it would have been most prudent to schedule processing of the transformer, dry out of the transformer. So given all of these uncertainties, which I know it's like, what do you do? But when you compare to previous test results, any observed change in power factor really deserves attention. But do make sure that you are comparing apples to apples. And this goes way back to what we mentioned earlier, is about don't ignore external influences. Because you're paying attention to any observed change, you have to make sure that any possible outside test variables are eliminated from what you're measuring. And again, these include temperature, test preparation, surface leakage on the bushings, and the condition of the bushings themselves. We've talked about test preparation and surface leakage, but let me just say a few things about temperature and the influence of bushings. So temperature is a big deal because power factor is definitely temperature sensitive. So for example, as a transformer cools after it's been removed from service for test, the power factor test result will change if the test is simply repeated at different insulation temperatures. So for a meaningful comparison between tests, all power factor test results need to be normalized or corrected to their equivalent 20 degrees C power factor value that adjusts for the influence of temperature. And this is the big but here. The challenge is that no single temperature correction curve will fit all cases because a dielectric thermal response, how it behaves with temperature, is not represented by a single curve for all conditions. Aging, moisture, contamination, they are going to all have an effect on how a bushing thermally responds. So temperature correction curves in use for decades are rendered invalid, and they themselves could complicate your analysis by introducing error. And in fact, some standards recommend discontinuing the use of these correction tables and curves altogether. There's an IEEE standard that has that specific language. So a more complete solution is to apply what's available today. It's an algorithm based on a dielectric frequency response, even a narrowband measure, and it provides an individual temperature correction. It's a unique correction based on the unique thermal characteristics of an individual transformer. So it takes into account how that transformer is aged, contaminated, and so forth, and gives exact correction back to what it would look like if you had the luxury to wait until the transformer cooled to 20 degrees C before you tested it. With regard to the influence of bushings, keep in mind that the active insulation of, for example, your high voltage bushings are included in the measure of CH. And the condition of the bushings may influence the CH power factor in this case for better or worse. Either way, in these cases, though, the condition of the materials inside the transfer tank is masked because you don't want it looking better than it is or worse than it is. The alternate is that the windings collective bushing insulation system may make up only a very small percentage of the total insulation being measured in, say, CH measurement. And so in these cases, any changes in the bushings conditions wouldn't notably impact the winding power factor, the CH power factor. So the only way to know whether bushings are impacting your results or not is to perform C1 tests on the bushings when possible, and then a simple calculation, which is nowadays automatic in most software. This simple calculation will effectively subtract the bushing insulation contribution from, for example, CH measurement. So any lingering question about whether your CH measurement in this case is off because of something the bushings are contributed, that question can be eliminated fairly quickly. And so do keep in mind that trending is the #1 way to analyze power factor or dissipation factor. When many test points are available, it's possible to filter outliers or erroneous data points that are a reflection of these variables: poor test preparation, incorrect compensation for temperature influences, or undesirable test conditions. And here I've shown a good example of a transformer that has had upwards of almost 40 measurements made on it through its life. It's a mobile transformer. And it shows the fluctuation that can occur in transformer power factor due to outside variables, including improperly correcting for temperature. And more or less, this transformer appears to be pretty steady, at around, upper 0.3 to 0.4% power factor. And so don't rely on general guidelines or power factor limits to analyze power factor results unless there's absolutely no previous test results that you can use. If there's no previous test results, these general guidelines exist to indicate approximately what a healthy power factor for an asset should be, as shown in the table on the slide. A transformer constructed with relatively low loss materials and that's subject to much care and handling during manufacture and assembly in the field should meet these limits. But beyond its use for these purposes, comparing to limits or to sister transformers or similarly constructed transformers as a tool to analyze power factor results throughout a transformer's life is just not recommended. Rather, power factor and capacitance values must be compared to previous measurements. And then finally, do be reassured that there are also well-developed suggestions for why power factor may have changed from previous results, such as shown in the table on this slide. And these also come directly from Megger's dissipation factor, power factor, and capacitance TLM bulletin. So sorry to go over here. I appreciate your time. This does conclude my do's and don'ts that I prepared for you today. So I have just want to end with 2 slides. And the first is to draw your attention to this resource I've been talking about. Megger makes these available to you free of charge. And these are, of course, our Transformer Life Management Bulletins. We've published 8 so far to date, as shown on the slide here. And then I've highlighted 4 of these that relate to information I've provided already in today's webinar, but I want to point out that these 4 will give you much more comprehensive information than I had time to share with you today. These are nearly monthly publications on various transformer topics. And if you sign up, you'll be automatically reminded every time a new one becomes available so that you can download it and add it to your library. And then finally, I will add too that Megger provides several power factor, dissipation factor, and capacitance test solutions depending on your needs. Shown on the left is our Delta 4000, which is our dedicated capacitance and power factor test instrument. Of course, it also does exciting current measurements. In addition to the features I've mentioned in the presentation today, the ITC for temperature correction, the individual temperature correction, and VDD, the voltage dependency detector, this instrument also has narrowband GFR testing capabilities. And moving over now to the right is our IDAC, and this is Megger's Gfr Test Instrument. It provides analysis of percent moisture content in insulation and dry insulation, also the oil conductivity, and it measures power factor, dissipation factor. It has some unique features that make it both extremely fast and at the same time highly reliable in high interference environments. And in fact, we're really excited to be celebrating the 20-year anniversary of the first commercially available Gfr Test Instrument. And we're really excited about how this instrument has more or less grown up or evolved in its incredible performance characteristics today. One more over to the right is the TRAX, and that's our multifunctional solution for transformer testing, as well as provides several common substation testing functionalities on breakers, instrument transformers, and protective relay components. It's actually not just another multifunctional test instrument, but rather many intelligent instruments built into one box. There is a difference. Its software includes a number of apps that make it fast and easy to perform a large range of different tests, but many transformer tests can be performed, including all of the functionality I mentioned present in the Delta with regards to the individual temperature correction, voltage dependency detector, etc. And finally, for the most demanding applications, we have the CDAC to the far right, which is a very high precision instrument designed for laboratory, production line, or even field testing of electrical equipment installation and insulating materials, as well as, for example, calibration of CCVTs and other ratio devices. So with that, this concludes my presentation. I thank you all very much for your time and attention. And Jamie, I'll pass it back to you now.
All right, thank you very much, Jill. At this time, the webinar is officially concluded, but we are going to get to a Q&A session here in a moment. I just had a couple of things I wanted to mention to you real quick. Okay. If you have any questions, you can still go ahead and submit those now at this time into the Q&A box on the right side of your screen. Also, for those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple minutes to provide your feedback so we can continue to improve upon future webinars. Also, a copy of the presentation as well as a video recording will be emailed to everyone later next week. All right, now let's go ahead and get to some of your questions. All right, first up, we have Volney Naranjo is one of our panelists today that's going to be helping out with some of the questions. And the first question is going to be for Volney. When testing, how do we avoid getting negative power factor, dissipation factor readings?
Well, during the presentation, Jill mentioned a couple of things related to negative power factor results. That is a common thing to get. It's an unrealistic result and could be caused by three different major things. One is design, specifically in circuit breakers with SF6 insulation. You will get it will be typical to get negative results. So it's a characteristic thing there, and you have to live with that. There's another situation in which you will get negative results, which is the insulation is definitely with a big problem. Something really bad is going inside the transformer or the insulation. Or the third situation is related to connections, which Jill referred to in the presentation. So it could be connections or it could be external contamination. So if this is something that you have never seen and you get this result in in one of your testings, you might want to check your connections, and you might want to check the condition of the external conditions of, for example, the bushings, to see if they're clean, that there's no moisture or humidity next to it, or these other elements. For example, when you have bus bar connected to the transformer that you cannot disconnect, that might be another reason you will be getting those negative power factors. So a little bit of investigation of what's going on around the testing environment, and see if you can correct those to improve the result.
Okay, thank you, Volney.
And Volney, well, Jamie, it's and Volney, if I may, I'll just continue and add to that as well. Since I was talking about transformers for so much time during this presentation, I will say that if you get a negative power factor for, like, for example, CH or CL or CT winding to ground insulation components, that is just simply not expected under any circumstances. So in those cases, that's when you would check the grounding of the transformer. Make sure, because that would probably be the one reason to cause that for CH, CL, or CT, is a grounding problem. You can check test connections too. Now, if you get it for an interwinding insulation system like CHL or CHT on a 3-winding transformer, high to tertiary, like I mentioned before with CL or CHL capacitance, where if you had a grounded shield between the high and the low windings, it would cause, the CHL capacitance to go down to this really small number, like 1 to 2 milliamps, which would be weird for a power transformer. Well, on the power factor side of that, that's capacitance / current. The power factor side of that could be the reason, because you're getting down to this really low current of capacitance, that could be the reason why you go negative for that CHL reading, or for CHT if it's because you got the low voltage winding sandwiched between the high and tertiary, which is grounded in the test circuit, looks like a grounded shield. That getting a negative power factor might be just indicative of the fact that you have that situation going on. And in that case, you're just going to really look at previous to make sure that if it's negative now, it was the same negative value before, and that hasn't changed. But another cause, and I mentioned it during the presentation, for a negative CHL is if, kind of by mistake or something, or something beyond your control. An example I gave was, so if you have a Y-connected low voltage winding and you don't disconnect that neutral terminal from ground, which you're supposed to do as test preparation to do these power factor tests, if you leave it connected to ground because you just simply forgot, or because it's under oil and you can't get to it, then that can also be a reason why you get a negative CHL reading. In my experience, the #1 time you see negative power factor is doing C1 measurements on bushings, and when you get too low of a power factor, if the nameplate is say 0.28 and you're measuring like 0.07% power factor, or it's gone negative when you're doing C1 tests on a bushing, I mean, surface leakage is 9 times out of 10 the culprit, and you really have to clean up that bushing and to see if you can correct it to a better power factor result.
All right, thank you, Jill. Let's get to the next question. This one's for Jill. Please explain why you get higher results with higher temperatures. And then part 2 is also, do you get higher or lower results if the connection is poor?
What, can you repeat part 2 again? Do you get
higher or lower results if the connection is poor?
Get higher or lower results if the connection is poor. Well, I'll start with number 2 since now I'm actually obviously just considering that at the moment. Poor connections. Connections are really crazy, and I could give you a lot of stories about poor connections and what they've done. They're very unpredictable in the test results. So yeah, unfortunately, I can't give you any rules of thumbs on what's going to happen with the connections being poor. Like, so for example, I'm thinking of testing a bushing, and it relies on a ground reference when you do, measurements. And if you're one of the culprits for a bad measurement is because that connection to ground is incorrect. Just like when you're doing a power factor test on the transformer, if that ground connection isn't proper, it can cause some really crazy things in your power factor results. In fact, not only can they go negative in that case, but then they can also go extremely high on the flip side. I've seen bad connections and surface contamination, for that matter, cause higher power factor measurements on bushings, and I've seen it cause lower. So there's no short answer to that question on which would cause, which would manifest. The high would result in higher power factors or lower if I have bad connections. I think it all depends on the circumstance, what you're testing, the application, and what the test circuit is, what it is you're measuring for that application, etc. So sorry for that I can't be more specific. With regards to temperature, you're absolutely correct that at the higher temperatures, this results in typically a higher power factor. And then because temperature is a stressor, and if I took anything, say I took somebody in good condition, and I'm like, hey, run as fast as you can this 100 yards, and at the end, I'm going to check your blood pressure. Well, even in perfect condition, that's a stressor, and it's going to elevate. And then, I could take somebody that's aged and not in good condition and have them run that same amount. I mean, and they're in tremendous distress because it's a stressor. So I'm elevating that blood pressure. So it's the same thing. And there's a more technical answer. And if you're really interested, we could talk about that offline. But with a higher temperature being a stressor, it's by default going to make, power factor, which is indicating how healthy that insulation is and its performance characteristics. It's gonna result in a higher power factor value.
All right, thank you, Jill. Okay, the next question is going to be for Volney, and that is, what type of instrument is used for a dielectric frequency response test?
Okay, in our case, we have actually 3 different instruments right now that can do DFR, dielectric frequency response. With our Delta 4000, we can do frequency response, dielectric frequency response from 1 hertz up to 505 hertz. That is what we call the narrowband DFR. Then we have IDAX, which is the instrument that we have for dielectric frequency response and the moisture assessment of the transformer. And with this one, it can go from 1,000 hertz down to the millihertz or even DC. And this is an advanced transformer testing tool to determine moisture condition and to determine the dielectric value of the insulation. And then of the oil. And then we have the tracks, which is a multifunction equipment in which we can also perform power factor tests from 1 hertz up to 505 hertz.
Okay, thank you, Volney. All right, next question is for Jill. What is the temperature dependence of the relative permittivity of a material?
Okay, well, this one is kind of caught me off guard. So this isn't going to be a straightforward one for me to answer. So these are great questions, by the way. Why don't Jamie, if you will, provide me with the person who provided the question, and if whoever provided the question, even wants to give a phone number, then perhaps we can talk about this a bit so that I can share some things, and then we can possibly lead into what I think is the answer to what you're talking about.
Okay, yeah, I'll definitely send you over their contact info so you can get in touch with them later, probably next week. All right, got another one for you, Jill. All All right, this person asked, did I understand that dielectric frequency response is a power factor test performed at multiple frequencies and may be a better indicator of moisture presence?
And the answer to that is a resounding absolutely yes. With the DFR, as it's called, dielectric frequency response, we're performing power factor measurements, upwards of 1,000 hertz all the way down to the millihertz region, and in some cases even low. But by performing power factor measurements at lower frequencies, this is a much better indication. I've got some excellent graphs, and so I will definitely expound on your question some more and share with you some really compelling graphs where you'll see that at line frequency, and one comes to mind that I'd like to show to you, but it, 3 DFR traces, one for a transformer that's very dry, but that has high oil conductivity, one for a transformer with exceptional oil, but it's very wet, and then one that's a service age transformer. And so you have the natural expected aging attributes of the solid insulation and the naturally expected aging characteristics of oil for the length and service of this transformer. And yet on this example, the 3 traces look extremely different, as they should, when you're comparing how power factor is changing with frequency, because there's some telltale attributes you're looking for on these DFR traces to make a determination about the source of the not great power factor results. But they all converge to a single point at line frequency. And while the power factor in this one example I'm thinking about isn't fantastic, I mean, it's somewhere on the order of 0.45% or close to 0.5%. That single power factor value doesn't really tell you anything about the potential source of why that power factor maybe isn't down at 0.3%. It could be that it's contaminated because the oil is highly conductive and has a lot of aging constituents in it, or it could be that there's moisture present in high amounts, or it could be, hopefully not, that you have a localized problem that's much worse if you could narrow down on the insulation where it's located, or it could be that it's just general aging, like I said, but you can't tell and differentiate from just that power factor value alone. So absolutely, the one thing that the industry has learned about a traditional power factor test and moisture is do not rely on it as an indication of how dry or wet your insulation system is. It's just not reliable for that purpose. Whereas DFR is absolutely what you need to be doing to keep track of, in this case, transformers, how wet your transformer population is. And you don't have to live in a wet climate to have wet transformers, because again, moisture is one of the byproducts of degradation and aging of solid cellulose and solid materials.
All right, thank you, Jill. We have time for about a couple more questions. Next one is for Volney. Could a change in transformer capacitance be due to winding movement?
Absolutely, as Jill showed at the beginning of the presentation when she was explaining the basics about the insulation. It's a capacitor, and the capacitance depends in physical characteristic or geometrical composition of the insulation. So the area of the insulation and the separation between the 2 elements that made up the insulation, that's going to be definitely affecting the value of the capacitance. So if there's any winding movement, any winding shifting inside the transformer, that is going to affect or going to change the separation between the windings, and hence the capacitance value. So, and that's one of the parameters you track whenever you are doing a power factor testing. As Jill mentioned also, capacitance is one of the values to not overlook or forget about, and we always track or trend that value as well as the power factor.
But just, if I may add, just one word of caution. In order for winding deformation to show up in capacitance, it has to be pretty pronounced, okay? It's not the go-to tool if you're concerned about winding deformation. If I look at capacitance and it's like, I haven't nudged a bit, same picofarads as I measured last time, I still wouldn't put that concern to bed yet. For winding deformation, for sure, the much more sensitive analytics for that and tools for that would be doing a sweep frequency response analysis test or doing a leakage reactance test. Either of those, both of those are exceptionally sensitive. In fact, leakage reactance testing is easier to see, in my opinion, winding deformation in a transformer than it is to see winding deformation in some SFRA traces. So just wanted to add that.
Okay, thank you, Jill. All right, we have time for one more question. This one's for Jill. Do you recommend performing a low voltage power factor test on a transformer that is no longer in oil but is still oil saturated?
Again, my personal preference is, well, first of all, why? Why would I be doing that? So that I would want an answer to that question. But, you know, yeah, I mean, if I'm doing it as a post-mortem test and I'm just trying to get some more information and maybe about why this transformer has failed and I don't care if I could potentially damage it or not, maybe. But if I'm doing it and I say that, I still would be exceptionally careful. There's a lot of different considerations you have to take in mind before you want to apply any voltage to a service age transformer, drained of oil, still of course oil saturated. You know, you need to look at combustibles in the tank. You need to look at clearances between, you know, what you're energizing and any other parts. You don't know what you're energizing, especially if it's an investigation of, you know, potentially failed unit. So there's so many reasons why that screams safety hazard. I have to be really sure that power factor and dissipation factor and capacitance had enough diagnostic prowess that it would make it worth my time to do it. And I'm not so sure that I'd be convinced of that. On the flip side, if this thing is just drained and whatnot, because I've been in the middle of a processing on the transformer, and you know I think it's dry, but I want to do a quick check on it and break the vacuum, and then do a power factor measurement to see if in fact I'm right. Well, power factor is not, once I get below 3% moisture content, which I hope my processing has brought me to that place, it's not gonna really give me much difference if I'm at, you know, 2.5% versus, you know, all the way down to a 0.5% moisture content in paper. So I'm just not getting enough information from the test to make it worth my while to, have to worry about all these other, you know, safety factors that I'm now introducing to the measurement. I would be turning to, I think, different diagnostic tools. There's a lot of diagnostic tests available for transformers that give me a lot of information. So it would be situational for sure, but my knee-jerk reaction to the question would be, no, I don't think I would do it.
All right, thank you, Jill. Looks like that's all we have time for today. I want to thank Jill for her awesome presentation, and also Volney for helping answer some of those questions for everyone. We apologize if we didn't get to your question today. We had probably over 40 questions, but we will follow up with all the questions offline, most likely in the next couple weeks. And also wanted to make you all aware that our next webinar will be on August 18th at 10 a.m. Central Standard Time, and that one is going to be titled Practical Applications of Cable Testing and Diagnostics Techniques, and that will be presented by Jason Sushak, Megger Cable Applications Engineer. We'd love to see all of you for that webinar as well. And that's it for today. Thank you very much. Have a great weekend, and please remember to answer the survey if you can.